Welcome again to Engineers Newsletter Live. I'm Jeannie Harshaw from Trane System and Application Engineering Group, and today we'll discuss all variable speed chilled water plants. This course is approved by the U.S. Green Building Council for 1.5 Green Building Certification Institute continuing education hours toward the LEED Credential Maintenance Program. After attending today's program, LEED professionals should submit their hours to GBCI. Today's program is also registered with the American Institute of Architects Continuing Education System and qualifies for Health, Safety, and Welfare credit. AIA members, please provide your member number to your local host before leaving today's session. And professional engineers, please check your state's rules to see if credit for attending today's program can be applied to engineers' continuing education requirements in your state. Now, while all variable speed chilled water plants are not a new concept, because of new requirements in energy codes and a greater focus on reducing energy use, we're seeing it used more and more today. Trane application engineers Lee Klein, Susanna Hansen, and Mick Schwedler will take us through a full discussion today. We'll start us out by addressing the drivers that brought us all together. We'll review some key takeaways from previous E&L programs that we'll build on during this program. Mick will dive into the potential efficiency of chiller plants and walk us through example configurations. Lee will follow and provide discussion on operation and control considerations, as well as user interaction. And Susanna will close out the discussion with applying variable speed to existing systems. It'll be another full program, so Mick, take it away.
So, what are our goals today? First, building owners, the government, ASHRAE, and USGBC are all focused on higher efficiency, and it's our job as practitioners to provide solutions. This leads to attempting to select the proper system components to give high efficiency at all operating conditions, that is, both full and part load, as well as full and part lift conditions imposed by varied system operating conditions. Now, some have applied variable speed drives to all system components, so we need to understand the effect of VFDs on those components. In addition, chilled water system control or operation is sometimes being outsourced. We need to understand that operation and especially its effects on system performance. So today, we'll be covering the system, the opportunity, and also the operation required to achieve energy and energy cost savings. Now, here's a historic graphic that shows the increase in ASHRAE 90.1 minimum chiller efficiency in terms of coefficient of performance, or COP. The two lines represent full load COP at AHRI standard conditions and the integrated part load value, or IPLV. Integrated part load value was first required by 90.1, 1999, so until that time, it's not plotted. Now, the difference in the 2010 Path B requirement is due to the IPLV rating points at 75% load and below having reduced entering condenser water temperatures. Later, we'll cover the effect that assumption has on a chiller with a drive. We see that required chiller full load efficiency flattened out, but there are more efficient chillers that can be selected. The last set of data are premium efficiency chillers, one selected for very high full load performance and the other selected to result in a high IPLV. So additional chiller efficiency levels are still available. In fact, over 20% higher full load or IPLV. Now, to further improve system performance, practitioners have looked to different components in the chilled water system, the pumps and the cooling tower fans. Now, before tackling system interaction, let's look at the chilled water system components historically. As variable speed drive costs came down and reliability increased, VFDs started to become more prevalent on all components in the system. Once use began, the results led to changes in standards and codes. Let's take a look at how these changes made their way into ASHRAE IES Standard 90.1 through 2010. A little later, Susanna will touch on changes for the 2013 version of the standard. Let's start with chilled water pumps. Now, when I began working in the industry in 1982, VFDs on chilled water pumps were being applied to the secondary pumps in primary, secondary, or decoupled systems. 90.1 1989 required variable chilled water flow in some systems, but only mentioned variable speed drive pumps as an option to respond to the variable flow requirement. In 90.1 1999 through 2007, there was a requirement for the chilled water pump to consume 30% of its design wattage at 50% design flow. Variable speed drives were mentioned as a technology that achieved this performance and were the technology used most often to comply with the standard. It's noteworthy that in these versions of the standard, the requirement only applied to pumps with heads that exceeded 100 feet of design pressure drop and with motors exceeding 50 horsepower. So it only applied to large pumps. In the 2010 version, this changed, with a threshold dropping to pumps exceeding 5 horsepower. So, from a practical standpoint, when was VFD-like pump performance required? Using the pump power equation shown here, we can back solve for capacity. For this example, we've assumed 75% pump efficiency and 2 GPM per ton, which is a 12-degree chilled water delta T. Through 2007, a VFD was not required on chilled water pumps until the chilled water capacity satisfied by that pump was 740 tons, and then only if both the pump head and power limits were met. The 2010 version brought that down to about 150 tons. But as you can see, the capacity threshold is dependent on the system pressure drop. Simply put, chilled water pump VFDs are prevalent today. Beginning with 90.1 1999, fan speed modulation was required for cooling tower fans 7.5 horsepower and larger. Often, VFDs were used to comply. Starting in the 1990s, variable speed drives began to be applied to chillers. From a standard perspective, 90.1 2010 added an additional compliance path for chillers. Project teams can choose either Path A or Path B. Once the path is chosen, both the full load and IPLV requirements must be met. Another thing to note is that these requirements are in the mandatory portion of the standard, so they must be met for every chiller, whether the prescriptive or performance method of compliance is chosen. Looking at the chiller requirements compared to Path A, the Path B values are about 2 to 4% less stringent at full load, but have a more stringent IPLV. Now, while I was the 90.1 chair, I really couldn't say this, but as an engineer, it sure seems that while Path B does not require a VFD, the performance requires imply that this path will generally be selected for chillers with variable speed drives. Now, let's look at the condenser water pump. The marketplace seems to be moving toward installing variable speed drives in lieu of starters. Then, since the drive is there, rather than using throttling valves, that VFD is used to balance the system, and there are energy savings since pump pressure is not being wasted by throttling. Next, since the condenser water pump already has a variable speed drive, the question being asked is, should we use the drive to dynamically change condenser water flow with the goal of further optimizing the system? It's probably the question I get asked the most today, and an engineer's newsletter on this subject was published late in 2012. We'll examine this topic in detail later. Now, for systems that include not more than 3 control valves, 90.1 2010 has no requirements for variable speed drive performance. Since in most chilled water systems, the condenser system has isolation and not control valves, 90.1/2010 does not seem to require VFDs on condenser water pumps in chilled water systems.
Now, one of the things we're going to be exploring today is the potential efficiency of chiller plants so that we can figure out how best to operate them. Now, as you look at your existing plants, what kinds of performance should you be looking for? One metric that seems to fall out of the discussion on chiller plant efficiency is kW per ton. Now, I'm not talking about an instantaneous metric, but an annualized metric, kWh per ton hours. And what are the relevant changes in 90.1/2013 that we can use to define what a minimally compliant chiller plant looks and performs like? Now, one way to think about how well your chiller plant operates is by some sort of a report card. Here's one that Tom Hartman came up with years ago. While the units are kW per ton, the fine print shows that this is an annual number. He doesn't say exactly how to calculate it, but he does give some guidance about the kinds of instrumentation required for collecting it. The performance scale suggests you shift the numbers slightly higher if you're using water-cooled screw or scroll chillers, because these chillers are generally a little less efficient, although we'll see in a moment that the gap is narrowing. Now, while it's nice to make generalized statements about chiller plant energy use, there are some obvious problems with the report card or performance scale approach in general. It doesn't matter whether the report card is this scale, or BTUs per square foot, or EUI, or some sort of in-situ building labeling program. How can you know what's possible? How do you compare to another office like yours, like with Energy Star? What if the office you're comparing to just lost their biggest tenant, or just sent their data and servers off-site? Are you comparing to many offices? What does matter is how you manage your own facility. How can you know what's possible for you? Now, while we must normalize to get rid of the effect of ever-changing loads and come up with a metric, we must also create a better way of predicting what excellent performance is at a given site. Let's focus back in on the chiller plant for a moment and the report card. We need a sliding scale grading for chiller plants. I'm talking about guidance that accounts for the plant configuration and the load profile. A lot goes into the load profile. For this case, let's just consider the building usage pattern or type, code minimum construction, climate, and the presence or not of air side economizing. The chiller plants shown in this graph all fall into the excellent scale because, on an annualized basis, their performance falls well below 0.7 kWh per ton hour. But as you can see, the climate and type of building makes a big difference. If I were the energy manager for this hospital in Chicago, unless there's some big real-world problem I'm working around, maybe I shouldn't be satisfied with 0.65 kWh per ton H. Here we see that our plant could have been over 35% better than excellent with the right chiller plant optimization method. And if I were looking to justify my salary as an energy manager, it would interest me to know that running my plant in an ideal state could be saving my employer over $100,000 over the course of a year's operation by getting to the true optimum and not 0.65 kWh per ton H. This chart shows annualized kW per ton for various combinations of climate and building type. We have Memphis and Chicago, an office and a hospital. Now, adding the second chiller alone does a lot for your annualized kW per ton. But as you can see, staging chillers at full load leaves room for improvement, especially once you get to more than 3 chillers, and especially in the hospital models. The red line is a Memphis hospital without air economizer and will be discussed later by Mick. So how do current minimally compliant chiller plants fare on this scale? To find out, we have to nail down some of the design assumptions that the code requires and fill in some gaps where there are no requirements. Now, on any scale, you'll see code minimum referred to. I'll get back to this in a minute, but in a nutshell, there is a lot of variability in the definition of a code minimum chiller plant. Let's turn to 90.1/2013's mandatory provisions, section 6.4. In the mandatory requirements, we have the first hurdle, equipment efficiency requirements. For centrifugal chillers, these requirements are modified for non-standard chilled water leaving and condenser leaving temperatures. For all other chillers, these are non-changing requirements calculated at AHRI standard test conditions, even if the chiller is applied at non-standard temperatures. There are scope limits for temperature that apply to all types of chillers. If a chiller is outside of the scope, then there is no minimum efficiency requirement and the chiller may be used without restriction. 90.1 2013 saw the first significant upgrade to the chiller efficiency requirements since 1999. Each chiller type, other than absorption, has 2 paths to compliance, each with a full load and a part load metric to meet. Here you see the air-cooled and positive displacement water-cooled requirements, and positive displacement would include compressor styles such as reciprocating, screw, and scroll types. The improvements in these categories include a new Path B for air-cooled chillers and a new category for water-cooled positive displacement chillers at or larger than 600 tons, with efficiency requirements for both paths that match the centrifugal requirements at or greater than 400 tons. As you'll see by comparing this slide to the next slide, positive displacement requirements are closing the gap with centrifugal chillers. In fact, the Path A IPLV for a 150 to 299 ton positive displacement chiller is actually more stringent than an equal capacity centrifugal chiller, but the full load requirement is less stringent. Large centrifugals were upgraded modestly, but there are some notable changes. Here you see that I've dropped the category for 600 and greater tons. That's because starting in 2015, the largest category of centrifugal chiller has been lowered to 400 tons. The rows in 2015 for 300 to 400 and for 400 and greater will be identical. It's encouraging that the best efficiency requirement for centrifugals starts to take effect at a lower capacity threshold. The more significant movements, though, are in IPLV, especially for Path A. These requirements apply only to chillers optimized at standard rating conditions. For chillers optimized at non-standard rating conditions, there are equations to use with a spreadsheet that the 90.1 committee created to generate the requirements for these chillers. The scope limits are the same as for 2010. In the mandatory requirements, we have the next hurdle, cooling tower efficiency requirements. Cooling tower efficiency is measured in GPM per horsepower at rated conditions. For the rest of today's presentation, we'll be focusing on systems using open circuit propeller fan cooling towers, the predominant type of cooling tower chosen for water-cooled HVAC systems. In 90.1 2013, propeller or axial fan open circuit cooling towers had the only change. They went from 38.2 GPM per horsepower to 40.2 GPM per horsepower. That's about a 5% increase in stringency. Next up, load and pump head calculations. How do you do your pump head calculations? We hope you're using something like Trane Pipe Designer software. We have heard lots of crazy ideas about how to size pumps, like the height of the building times 2. We don't recommend this, and neither does the code. It's actually a requirement of 90.1 to use generally accepted engineering practices for calculating not just load, but also pump differential pressure for the purposes of sizing the pumps. Here's an excerpt of what 90.1 says. The pressure drop through each device and pipe segment in the critical circuit at design conditions shall be calculated. Now that it's common to have VFDs on pumps, the drive is used to balance the system. But if your pump VSD has to be turned down to 45 Hz at the design point, not much additional turn down is available. Likewise, if your load calculation is poor, especially if it's dramatically oversized, your chiller plant won't be as efficient as it could have been and also overpriced. I'm going to skip over piping installation as there were no changes in this area in the 2013 version. The prescriptive section of the code tells us many things to expect our control system to coordinate. There is a new addition for 90.1 2013 for hydronic systems. This new twist is the requirement for either pump pressure reset, formerly the only compliance method, or chilled water reset. You will turn the set point up or down based on the critical valve being nearly wide open or until you reach the design limit of the system. The set point would either be pump differential pressure or temperature. Variable flow is required on hot and cold water systems once you have more than 3 control valves. This means you are required to have provisions to reduce flow to 25% of design flow or the equipment limits. In systems with pump motors larger than 5 horsepower, you are further required to use variable speed drives or equivalent performance on the pump motor. And how much you're pumping matters too. Pipe sizing limits in the form of GPM per pipe size ensure that excessive pump pressure and pump energy is avoided. Cooling tower fans, larger than 5 horsepower, are required to have VFDs or similar performance, and the new part is that VFDs are required to be operated together across all operating cells, and that towers have a 50% turn down capability. Another new change that kind of flew under the radar with respect to chillers is the new lower limit on hot gas bypass. This is a design element for chillers that has a valve that can open at low load to false load the compressor and keep the chiller either away from surge or keep the chiller idling online while its application prefers that the chiller not turn off, usually at very low load conditions. The big problem with defining the code minimum chiller is that several design choices have no requirements. For example, the 90.1 prescriptive path does not have a requirement for a certain delta T or flow rate. Only the performance path defines these. The performance path budget for chilled water pumping is 22 watts per GPM for chilled water pumping and 19 watts per GPM for condenser water pumping. The prescriptive path is silent on delta T and how much water to pump. However, a 12-degree delta T, 44 to 56, is the baseline for calculating lead performance and possible credits. Other areas where there are no requirements include chiller turndown and surge resistance. Tower temperature control, as Mick will show us shortly, is very important. Configurations, system controls, staging, and types of chillers to use for various applications are also areas where the designer is permitted to use his or her discretion. But these decisions affect chiller plant performance a great deal and lead to a range of minimally compliant chiller plant performance, as if building type, climate, and other factors didn't give us enough variability. You may be asking, how did the 90.1 committee and the team from the Pacific Northwest National Lab model the stringency improvement from one version of the code to the other? Well, we used standard design practice for system selection and guidance from the performance path baselines in the absence of prescriptive requirements. If you turn the crank on that model, the minimally compliant chiller plant just meeting 90.1 2013 requirements and using good design practice for decisions where there are no requirements leads to a chiller plant that will be quite good in annualized energy consumption in kilowatt hours per 10 hours. In reality, though, there is no certain answer to how well the typical chiller plant actually operates today, even if it does meet code. Our models show that it's possible to be excellent, that is, below 0.7 annualized kW per ton, while only just meeting code minimum requirements today using constant speed chillers and a fixed tower set point. Code minimum performance on an annualized system kW per ton basis hinges on the number of hours of operation in the spring and fall and what fixed tower set point you select. As we showed in the earlier chart, 20% improvement beyond the code minimum is still available, both for full load and part load.
Thanks, Susanna. Back in 2006, we presented an ENL on variable speed drives and their effect on system components. It's available for online viewing at Trane.com educational resources. Maybe some of you went back and viewed it in preparation for this presentation. For those of you who did not, we'd like to review a few highlights that will help with the concepts being presented here. First, we all know and love the myth that when you add a VSD to any device, its power use immediately decreases with a cube of the load reduction. The reason it's a myth is that most people use the word load as synonymous with speed and assume it makes no difference. But there is a big difference. The load on the device has two factors, the mass flow and the pressure rise. The only time a variable speed device's power use will fall with the cube of the component's load is if the pressure across the device falls to the square of the load. Very few applications follow this principle of operation. Let's see what we discovered in the previous Engineers Newsletter. The performance of dynamic variable speed devices such as centrifugal fan wheels or pump and compressor impellers follows the affinity laws, which state, as the speed is reduced, the flow through the device decreases proportionally. The available pressure rise from the device, also known as lift, decreases proportional to the square of the speed reduction, and the power use then decreases proportionally to the cube of the speed reduction. These principles apply only to the fan wheel or impeller operating by itself. In reality, a variable speed device is almost always part of a bigger system, and the operating characteristics of that application will dictate how the device performs. Let's look at a few applications and see how this plays out. Cooling towers are free discharge devices. The air path resistance is almost totally due to frictional losses. There is no fixed lift or variable dampers to influence the airflow resistance. Even so, the power draw of a cooling tower fan does not exactly decrease to the cube of the tower load. The blue line on the chart represents the fan power decreasing to the cube of the fan speed. The red line represents an example of a cooling tower's actual performance if controlled to an 85-degree set point, which would reduce the fan speed as quickly as possible. As you can see, it's close to the ideal performance, but not quite that good. This is because there are other things going on in the tower that influence its performance. Things such as water and airflow patterns and evaporation rates. Even so, a cooling tower is probably the component of a chilled water system which operates closest to the ideal cube of the speed power reduction with load. Chilled and condenser water pumping systems both have a fixed or controlled pressure component and have a minimum flow requirement. These prevent the pump energy from following our ideal curve. Specifically, in many variable flow chilled water systems, there is a system differential pressure set point the pumps must meet. Depending on the pump control logic, that may be fixed or somewhat variable. Also, there is a minimum allowed chiller flow which prevents the system flow from following the system load curve to zero. For condenser water systems, the lift from the tower sump to the distribution nozzles is a fixed value, and cooling towers too have minimum flow requirements. The chart shown here provides an indication of how these fixed pressures and minimum flow requirements prevent the pump's power draw from following the ideal curve. The good news about chillers is that a chiller compressor's load does follow the system load down to a very low value. The bad news is that the lift the system imposes on the compressor seldom decreases anywhere near to the square of the flow as would be required to achieve the ideal speed and power reduction. The reduction in compressor lift is limited by a number of factors. The first is outside wet bulb temperature. The system condenser water temperature can only decrease if the wet bulb temperature decreases. We've begun to term this as the wet bulb opportunity. As I'm sure you understand, this wet bulb opportunity does not necessarily follow the chiller's load profile. Additionally, if the speed of the cooling tower fan and condenser water pump are reduced to save energy on those components, the chiller's leaving condenser water temperature is elevated, limiting the chiller's lift reduction. The bottom line is that the load and lift do not necessarily decrease in the correct proportion to allow a centrifugal compressor to approach the ideal speed and power reduction. Don't get me wrong, I believe adding a VFD to a centrifugal chiller's compressor almost always saves chiller operating energy on an annualized basis. But it is not always the most cost-effective place to spend our energy investment dollars. There is one other caveat that should be pointed out. In this E&L, we are talking exclusively about dynamic flow devices. Positive displacement devices, such as screw or scroll compressors, do not follow the same load and lift relationships. We'll save this discussion on their operating performance for a different day. In the 2006 E&L, this chart was shown as an example of how the various components in a chilled water system might unload under a specific set of conditions and control sequences. There are two things to take from this chart. First, all the components unload somewhat differently and not to the cube of the speed ideal. And second, if the components of the system were unloaded as shown, it would be an efficiently operating system. Unfortunately, this is seldom the case in most systems, nor is it quite that simple. But with proper control, we can do significantly better than is typical today.
Thanks, Lee. Let's fast forward 5 years. Here are some takeaways from our 2011 Engineers Newsletter Live on upgrading existing chilled water plants. Adding a variable speed drive to a centrifugal chiller benefits operation when there are enough operating hours at low lift conditions. For example, when the tower water temperature can be reduced. If the chiller is to be replaced, compare two chillers with the same price, one with a variable speed drive and the other with more heat exchange surface and therefore premium efficiency. Perform an analysis with both demand and consumption costs. Cooling tower fans are often a great retrofit application for VFDs. From a chilled water pump standpoint, there's low-hanging fruit for applying VFDs, especially in constant flow systems. From a retrofit and controls perspective, rather than converting from a primary secondary to full variable primary, a more cost-effective solution may be to convert to variable primary, variable secondary. If air handling valves have direct digital control, use that valve position to optimize pump pressure at all operating conditions. And use a VFD on the cooling tower fan to optimize the sum of the chiller plus tower energy consumption. We'll see quite a bit more about this today.
As we discussed in the 2011 broadcast, you need to determine whether or not dynamically changing the condenser water flow rate should even be considered. If you've already minimized the condenser water pump kW, for example, by reducing its design flow rate to 1.5 or 2 GPM per ton, it may not even make sense to take the time to look further. The pumps already have a really low contribution to the chiller plant energy picture. If you already have VFDs on your cooling tower, reducing the tower fan speed dynamically can achieve a lot of the potential savings, and it's simpler. But if you do decide to reduce flow, there are limits to consider, and Mick will be talking about that in a few minutes. Some of the limits include the minimum condenser water flow rate, not only from the chiller's perspective, but also from the towers and the pump's perspectives. As you examine combinations of load and flow rate, you'll need to identify limits that keep the chiller out of surge. And as we mentioned in 2011's broadcast, documenting the sequence of operation and assisting with the commissioning of the system should be required of anyone dynamically modifying the condenser flow rate.
Okay, we've done an overview of what's been covered on past E&Ls. Now let's start putting some numbers on various system options and control methods. Since in past E&Ls we've spent so much time on the chilled water side, we're going to concentrate on the condenser water side today. We'll examine building types in 4 locations. Shown here is our base system configuration for the office building in Chicago. The building has an airside economizer, so during many hours of building operation, the chilled water plant will be off. Note the design condenser flow rate of 3 GPM per ton is something we'll reconsider, as are the chiller type and cooling tower set point. Since we often see building operators use a fixed set point, our base reflects that. As alternatives, we'll add a VFD to each component. We'll also consider a lower design condenser water flow rate. Then we'll examine just tower controls and a combination of condenser water pump and tower controls. For our analysis, we'll calculate the annual energy usage in the system in terms of kilowatt hours. We'll also calculate the annual system ton hours. For example, a chiller operating at 300 tons for 2 hours must provide 600 ton hours. Our annual performance metric today will be kilowatt hour per ton hour. That is the annual system kilowatt hours divided by the annual system ton hours. By canceling the hours, we'll shorten the term to annualized kW per ton for the chilled water system. For each alternative, we'll have the following monikers on the chart. For chiller type, constant speed or variable speed. Cooling tower fans, either single speed or variable speed. When a chiller is added, so is a cooling tower fan. Condenser water pump design flow rate in units of GPM per ton. The condenser water pump, either constant flow or variable flow, and when a chiller is added, so is the condenser water pump. Finally, there are many cooling tower control methods. Today we'll compare fixed set point control and optimized control. We designate the fixed set point control by showing that set point For example, 85 degrees in the table. The base case is a constant speed chiller, single speed tower fan, condenser water design flow rate of 3 GPM per ton, a constant speed condenser water pump per chiller, and a tower control to maintain 85 degrees. For this system, we analyzed performance with 1, 2, or 3 chillers. The annual kW per ton was drastically reduced with more chillers, but the difference from 1 to 2 was significantly greater than from 2 to 3. Now this makes sense, since the chillers themselves will likely operate in a more efficient mode, and ancillary energy consumed by constant speed equipment is much higher for 1 large chiller than it would be for 3 smaller chillers. Our next alternative only optimizes the cooling tower set point. We see that this reduces the annualized kW per ton about 0.1 in all cases. So our first conclusions are that multiple chillers improve system efficiency and optimal tower fan control saves energy. The next alternative begins with the base case but applies a variable speed fan to the cooling tower. Just putting a VFD on the cooling tower fan reduced energy consumption more than applying optimal control to a fixed speed tower fan. We can see why 90.1 required tower fan speed control back in 1999. Now we'll take this same system and optimize cooling tower fan control. Again, there's a significant savings simply by dynamically finding the optimal tower set point. Frankly, performance is beginning to look pretty decent on an annualized basis. Now, some people might stop here, but there's still some low-hanging fruit to be picked. For these 2 alternatives, here are our conclusions. It's no surprise that since cooling tower fans are free discharge fans, their savings are nearly cubic and that they're a great efficiency measure. And we again see that optimal tower fan control is a significant energy saver. But let's make the system performance better yet. Today, many people select chillers with variable speed drives. So let's look at that option and compare it with a constant speed chiller. Here's the performance. Worse than a similar system with a constant speed chiller. No matter how many chillers are operating, the performance is less efficient. This looks surprising, but it takes us back to the basics of a variable speed drive on a centrifugal compressor. The lift the compressor must overcome is proportional to the difference between the condenser leaving water temperature and the chilled water leaving temperature. In order for the drive to slow down, the compressor lift must be reduced. Assuming a constant chilled water set point and a tower control to maintain its design temperature, the leaving condenser water temperature only changes a little. And that change is proportional to the load and the design delta T. This change is not enough to offset the inefficiency of the variable speed drive. This shows us that it's imperative to apply chiller variable speed technology appropriately and that proper system design and control are critical. So, let's do that by applying optimal cooling tower fan control. Note the huge change from improper tower fan control in all cases. So from an energy perspective, optimal tower control has a significant reduction, in line with that of VFDs on cooling tower fans. Our conclusions are that the tower fan control is critical when variable speed chillers are installed, and once again, optimal tower fan control saves significant energy. Now this is the 3rd time we've reached that conclusion. Perhaps it's time for optimal tower set point control to become another fan law. From here on, all our alternatives are going to use optimized cooling tower fan control. Next, let's look at changing the design condenser water flow rate. Since we're looking at strictly energy consumption, when we reduced the condenser water flow rate, we left the pipe sizes the same, and use the same cooling tower fan. Reducing tower flow rate results in reduced condenser water pump power and energy, as well as a closer cooling tower approach temperature. The result shows lower design flow rate provides very good savings for fewer chillers. But as the number of chillers increases, performance differences are less significant. This lines up with the industry's understanding of flow rates. Steve Taylor wrote a chilled water system article published in the December 2011 ASHRAE Journal. In his analysis, pipe sizes were reduced, which also reduced some of the possible condenser water pump energy savings. However, this quote from the article's summary states that increasing the condenser water delta T, that is reducing the flow rate, is a life cycle cost saver. By the way, that last clause shows that this is true for all chiller manufacturers. Now let's put a variable speed drive on the condenser water pumps of a system using the older 3 GPM per ton design flow rate. There are some savings due to proper control of the VSD, but the system performance is very similar to that of a system that was designed with reduced flow and used a constant speed condenser water pump. So design teams can choose to design with lower flow rate and simpler controls, or higher flow rate and increased complexity. Results are similar. The final option is design with a lower condenser water flow rate and optimize the condenser water pump control. So for the bottom points, the condenser design flow rate is 2 GPM per ton, and a VSD has been applied to the condenser water pump. As expected, the system performance is better, but only a little bit. So as Susanna mentioned when summarizing the 2011 E&L, reducing condenser design flow rate may allow high performance without increasing condenser water control complexity. So going back to the previous conclusion for condenser water design flow rates. Designing for a lower flow rate, for example, 1.5 or 2 GPM per ton, gives very similar performance to a system using an unoptimized condenser water design flow rate of 3 GPM per ton and dynamically optimizing the condenser water flow rate. So let's summarize all the conclusions. Multiple chillers improve system efficiency. Optimally controlled variable speed tower fans save a lot of energy, and that control is absolutely critical if variable speed chillers are applied. Proper design condenser water flow rate is important and allows simple condenser water control. And variable speed condenser water pump control can save some energy, but primarily on over-designed systems. So, this is for an office building in Chicago with an economizer. Do similar conclusions hold in other climates for other building types? We don't have the time to examine every climate or building type, but let's look at a few more. First, a hospital without an economizer in a more hot and humid climate, in this case, Memphis. Here are the side-by-side comparisons of the two buildings and locations. While the actual performance in terms of annualized kW per ton is different, the similarity of the direction and proportion of changes is striking. Here is the Memphis hospital performance only. Given that the shape of the performance is so similar to the first building, we come to the same conclusions. Adding a second chiller is important. Variable speed drives on cooling towers is significant. Optimal control of cooling tower fans is imperative when variable speed drive chillers are selected. And again, low flow design condenser water flow rates give very close to optimal performance even without condenser water pump speed control. So let's try a dry climate with an economizer. Here's an office building in Albuquerque. Again, the trends look very similar. We started asking ourselves if there is any climate where there is a difference. Let's look at an office without an economizer in Miami. The only thing we see different is that in this climate, reduced design condenser water flow rate, 2 GPM per ton, gives more savings. However, there are virtually no savings from variable speed condenser water pumps. So after looking at this limited set of buildings and locations, the conclusions reached are the same as what was already covered. A possible exception is that variable condenser water flow rates may not save energy in very hot and humid climates. Lee, what's next?
There's a lot of buzz in the industry surrounding the control of chiller plants, and particularly all variable speed chiller plants. Most of the current offerings are fairly tightly sealed black boxes. The goal of this part of the E&L is to open up the box a bit and discuss the most important characteristics of such control. As I think you're hearing from this E&L, one thing that has become apparent is that you don't necessarily need a VFD on every motor in the chiller plant to have an efficient plant or to apply some of these control and optimization methods. The first and most important factor of chiller plant operation is balance. As Mick has shown, the system efficiency is greatly influenced by the design conditions. Said another way, if the design conditions are properly balanced, there is much less excess energy to be controlled out of the system. From a control point of view, the ongoing goal is to properly balance the component energy use as the load and operating conditions change. Let's see what this might look like. I'm sure you still remember this chart of unloading performance we showed earlier. I suggested it represented balance control for an imaginary set of conditions and would result in efficient system operation. Let's see what unbalanced operation might look like. What if we set the condenser pump to provide design flow and the cooling tower fan set point at 55 degrees? On this chart, we can actually see what would happen. Such operation would result in the fans and pumps running at 100% speed at most conditions. The pump and fan power would rise significantly relative to the system load. The result is that the chiller condenser would get a higher flow of cooler water, which would reduce the compressor's lift and energy use. The question is, what would happen to the system energy use? Past analysis have provided this answer. The system power would go up, in typical cases between 5 and 10%. This control sequence does not take advantage of the opportunity of the rapidly decreasing fan and pump energy intensity in the 100 to 80% speed range. The chiller's limited decrease in power use cannot compensate for the rapid increase in fan and pump energy use in this range. What if the control sequence slowed the condenser pump significantly with a cooling tower fan set point of 85 degrees? The pump and fan power would drop at most loads. The chiller condenser would get a lower flow of warmer water, which would increase the compressor's lift and energy use. Again, the question is, would this lower or raise the system energy use? Mick's earlier analysis had the answer. The system power would go up. In the examples he analyzed, between 5 and 10% again, from a fully optimized system. The chart demonstrates why. This sequence does not take advantage of the greater flow available at very low energy intensities from the fan and pump at the relatively low speeds. This sequence results in a relatively large increase in chiller power use, which overwhelms the minimum fan and pump savings. There are 3 keys to achieving operation in the system's energy balance sweet spot. The first is to eliminate parasitic losses. A parasitic loss is a process where energy is consumed, but no useful work is performed. A perfect example of an avoidable parasitic loss is a throttling valve, such as a triple duty valve on a pump. When a VFD is used to control a pump, there is seldom a reason for the waste and cost of a triple duty valve. Even if active variable flow is not planned, the pump speed can be adjusted to commission the pump flow at a greater savings over the triple duty valve restricting flow. We've been in a number of chiller plants with the VFDs on the pumps running at 60 Hertz and triple duty valves cranked 30 to 60% closed. It's a sad waste. Although it's not often thought of as such, another form of parasitic loss is a constant pressure set point on a pump or fan. Using a constant pressure set point requires control valves to consume excess part load system pressure that the pump expended significant energy to create. Using a set point optimization method such as critical valve optimization considerably reduces this form of parasitic loss. One last form of parasitic loss to talk about is excess flow. Again, not often thought of as a parasitic loss, sending chilled water out in a variable flow system only to have it flow through a bypass wastes work performed by both the chiller as well as the pumps. Allowing an airside system to operate at a low chilled water delta T is a form of unmanaged parasitic loss. Increased flow packs a twofold penalty to energy consumption. The increase caused by greater mass flow, along with a greater system pressure requirement as a result of the pump energy rising to the cube of the parasitic flow increase. While as exciting as some other optimization methods are, eliminating parasitic losses really needs to be the first step in optimizing the energy use of any system, variable flow or not. Without this, the effectiveness of any other optimization technique will be substantially limited. The second step in controlling to the energy balance sweet spot is proper component sequencing. While adding variable speed drives to system components does not always dictate changing the sequencing logic, there are circumstances where a change in sequence can result in appreciable savings. Let's examine the effect of adding variable speed drives on the sequencing of two different components. First up, cooling towers. Here's an example of a typical two-chiller, two-cooling tower condenser water system operating with one chiller and one tower near design condition. Note that it's designed with an energy and installed cost optimized 15-degree delta T, about 2 GPM per ton. At design conditions, the cooling tower fan operates at the full fan speed of 60 Hertz and draws 15 kW. This is somewhat of a repeat of the 2006 discussion, but I think it bears examination. What if we changed the cooling tower sequence on the system and ran both cooling tower cells to meet the same operating conditions? If we ran both tower cells, they would each receive half the design water flow. By operating both fans, they would meet the same system operating conditions at approximately 30 Hertz. If you run a tower selection, you'll find it's not exactly 30 Hertz, but for the sake of this illustration, it's close enough to make the point. What would be the power draw of two free discharge cooling tower fans meeting the same conditions as one? If we do assume the ideal case and assume energy savings to the cube of the load, we would see that the power draw of each fan would be approximately 1.9 kW. That makes the power draw of both fans together 3.8 kW. That's a fan energy savings of over 70% with no negative impact on the performance of any other part of the system. If we plot the one tower and two tower fan performance on the unloading chart, we can see the potential fan power savings at various tower loads. But what's the catch? Because there's always a catch. For this specific example, there are two. One, the cooling tower cells must be specified and selected for operation down to 50% or less of design water flow. Any cooling tower manufacturer can meet this requirement, but it must be specifically requested. Often, even existing cooling towers can easily be retrofitted for more flow turn down. The second catch in running additional tower cells is a bit less obvious. Let's look again at the unloading curve. Same slide, but with an added operating line. This line is the power draw of two fans operating at 60 Hertz. As you can see, the total fan power skyrockets to 200% of the original design intent for operation with one chiller. This would happen if the operator manually overrode the fan control set point or drive speed. While this would provide somewhat cooler supply condenser water, the resulting power saving from the chiller could not come close to offsetting the excess power consumed by the tower fans. This is one of the key risks of adding a VFD to a component. It may save energy, but it may result in significant energy loss as well. Let's move on and look at the sequencing of chillers with variable speed drives. It will turn out to be a little more interesting. Let's look at variable speed drive centrifugal performance from 3 perspectives: how they unload with constant lift, how they react to reduced lift, and then what are the control implications. Here is the unloading line of a variable speed chiller selected and being controlled to a constant 85-degree entering condenser water. What is interesting about this line is that if you compare it to the unloading line of a constant speed chiller, it would be very similar. The fan laws tell us why. If the compressor slows down, the impeller's ability to create pressure falls with the square of the speed. Since the condensing conditions are not allowing the chiller's lift to decrease, the impeller's speed must be kept high to meet that lift requirement. But if the cooling tower is able to provide 10 degrees cooler condenser water, the compressor can begin to leverage its variable speed capability, as shown by the yellow line. 20 and 30 degrees cooler condenser water enables even better chiller efficiency, as shown by the green and blue lines, although at a slightly lower incremental savings per degree cooler water. It should be noted that constant speed chillers' efficiencies benefit from cooler condenser water as well, just not as dramatically. What do these unloading curves imply about sequencing multiple chillers? Here again is the design condenser water temperature unloading curve. If one chiller is running at full load, it will draw approximately 0.55 kW per ton. If at the same condenser water condition we turned on a second chiller and share the system load so that 2 chillers are each running at 50% load, they would run at a less efficient 0.58 kW per ton. We would have to evaluate the whole system's energy use, including all the pumps and fans to be sure, but it's likely that running 2 variable speed chillers at half load with high lift would result in less efficient system operation. One other element that comes into play is chiller operating stability. It's very probable that many single-stage centrifugal compressors would experience unstable operation, that is, surge at 50% load and design entering condenser water conditions, without some other action such as hot gas bypass, which should be avoided as much as possible. But what about at other operating conditions, namely lower lifts? Here, we see the unloading curve with a 20-degree decrease in entering condenser water temperature. The curve not only drops, but it cants downward to the left. At this condition, one chiller at 100% load operates at 0.39 kW per ton, while if 2 chillers were running at 50% load, their performance would be 0.30 kW per ton. This represents a 23% reduction in chiller energy use for the same system load. Again, it would take a complete system analysis, but with sufficiently reduced lift, it certainly appears that there are times when running 2 variable speed chillers would be better than running 1. The specific chiller's unloading curve, the system design, and other component operating limits combine to make optimally sequencing variable speed chillers a complex task. The challenge is to take advantage of the opportunity while keeping it understandable to the plant operators. Another topic that does not normally come up in the discussion of component sequencing is the importance of stability to system efficiency and reliability. One of the reasons I mention it here is that there are optimization strategies that depend on a method of regularly turning things on and off to see if it results in more efficient system operation. This methodology would make you believe that optimization is unpredictable. However, it is predictable, and such trial and error methods ignore the fact that even with VFDs acting as motor soft starters, every operating cycle introduces system transients that result in additional wear and tear on multiple system components. A second and more common stability issue is unstable condenser water temperature control loops. It seems these occur quite often with no one concerned with the impact on equipment or system performance. Let's examine a couple examples of why stable control needs to be a priority in variable speed chiller plants. Shown here is a simplified version of a centrifugal compressor map. The horizontal axis is load, and the vertical axis is head or lift. On the right, the compressor map is bounded by the black capacity line. This is the highest capacity the compressor can produce at a given speed and inlet guide vane position. On the left is the red surge line. This is effectively the lowest capacity the chiller can produce. Attempting to operate to the left or above this line will result in unstable, surging operation. The dotted blue lines represent lines of equal efficiency, sometimes called efficiency islands. The top curve represents the best compressor efficiency with decreasing efficiency at lower islands. Here's the same compressor operating at a lower speed. It has a new map, and as would be dictated by the fan laws, at lower speed, both its capacity and pressure rise or lift capability are reduced. And here's the compressor operating curve at even lower speeds. As expected, the greater the speed reduction, the lower the compressor's capacity and head producing ability. Let's use these curves to help understand the impact of unstable condenser system operation. Here we see the compressor operating at part load and part lift. The blue dot represents the chiller's operating point as dictated by the system load and the condenser water conditions. The chiller control reduces the compressor's speed to match the system's load and lift requirements as efficiently as possible. Under some conditions, the controls might have to additionally adjust the inlet guide vane position to perfectly match the load, but we'll ignore that for now. At this load point, the control is causing the chiller to operate stably and efficiently at about 52 Hertz or 87% of design speed. It's important to note that the most efficient operating point for the compressor is tucked up as close as possible to the surge line, right on the edge of surge. This discussion of why this is true is beyond the scope of this E&L. There are other presentations available that explain this in some detail. In effect, it's kind of like visiting the Grand Canyon. The best place to take a picture is standing next to the edge of the cliff. But be careful if your wife asks you to take just one more step back. But I digress. Now, what happens if the condenser water conditions suddenly change? What if the tower controls suddenly slow down or cycle a fan off? The cooling load does not change, but the condenser water temperature rises. The increased condensing temperature simultaneously raises the lift required of the compressor while slightly reducing its capacity. If the chiller controls cannot keep up with the changing conditions, the result is that the compressor is forced into a surge condition. Surge is noisy, it scares operators, and it's inefficient, and worst of all, if it's severe enough and continues long enough, it causes damage to the compressor bearings. All in all, this is not a good thing. For this reason, the chiller's controller is programmed to rapidly react to the surge condition, speeding up the compressor to restore stable operation. If the system were operating at its peak efficiency at the previous conditions, then by definition, this is likely a less efficient operating point. Let's look at the impact of the opposite form of instability, rapidly decreasing condenser system temperature. Just for the sake of the example, let's say the system conditions are requiring the compressor to operate at this point. Now, what happens when a cooling tower fan is turned on or quickly ramped up in speed? The condenser water temperature drops, causing the required compressor lift to drop as well. This would not cause surge, but the compressor capacity rises slightly, causing the leaving chilled water temperature to drop below set point at a lower compressor efficiency. A chiller's control number one priority is to safely meet the leaving chilled water temperature, so the controls would immediately begin to reduce the inlet guide vane position and the compressor speed to restore the proper chilled water temperature. In a short period of time, the load would be back under control. This is all fine, and the chilled water load would be met without any problem to the system, but at any time the chiller controls are forced to chase significantly unstable tower control or unstable chilled water return temperature or flow is time when the chiller and system are not operating at peak efficiency. For that reason, and to prevent undue wear on system mechanical components, we want our system control to place a priority on stable operation. Let's look at the last key to achieving balanced and optimum system efficiency. That is component capacity control. As we suggested previously, the key to system efficiency is balancing the energy investment in each component at that moment's operating condition, all while avoiding operation outside of any of the component's acceptable operating range. As with mixed system analysis, we'll look at condenser system control options as an example again, because it is the most universal application and often the greatest opportunity for savings. Shown here are three often implemented methods of condenser water system capacity control. You can read the short list of pros and cons for each method. In general, all of these control methods share a couple deficiencies. First, they are all based on some single fact that has been improperly stretched into an optimizing philosophy. Here are a few examples of what I'll call these improper so statements. The system is designed with an 85-degree entering condenser water temperature, so that must be the right place to run it. The chiller benefits from cooler condenser water, so let's set the condenser water temperature set point to 55 degrees and give it as cool as possible. The tower is selected with a 7-degree approach, so it should run according to that. And finally, the chiller has a minimum allowed refrigerant differential pressure, so that must be the best condition to operate it. I think you get the idea. A second shortcoming of each of these control methods is that they don't provide a clear path to coordinated operation of multiple competing components. In the case of a condenser water system, that would mean energy investment in the cooling tower fan versus the condenser water pump. However, these methods do have one huge strength. That is, operators are familiar with them and they at least think they can relatively quickly and easily troubleshoot them. Whatever else might be implemented, it is very important it can be easily understood by operators in a way that makes them comfortable and confident in its operation. So then, what control can coordinate the energy use of the various components in the system? If, as we indicated before, the optimum system operation occurs when each component's energy intensity is scaled to the system load, then it seems it would make sense to use the system load as the primary variable of control. In the world of advanced technology, this is what is termed a duh moment. Of course, every duh moment needs to be followed by analysis of will it really work, and most importantly, when will it not work? So what are the potential pros and cons of this concept of load-based system control? The potential advantages of this method of control are really what we've been discussing. It provides a method to balance the allocation of energy intensity scaled to system load. The key then is proper scaling of the component operation versus system load. How is this scaling calibrated relative to full load operation? Should the scaling method be linear, or is the relationship more complex? What you find is that the answers to these questions change based on the system design parameters as well as each component's performance. The analysis is not trivial, but it's not impossible either. A secondary benefit of this method of control is that when properly implemented, it enhances control stability compared to more traditional methods. However, it does not come without other challenges. This form of control, if not constrained properly, can and will drive one or another component into an unacceptable operating region. Mick will discuss component operating limitations in just a moment. Suffice to say that it is imperative that an implementer of this control method have a thorough understanding of each specific component so that the control sequence can be properly constrained. We don't want to overstate this requirement. Every control method comes with constraints, but since this is new and an unfamiliar control method, it is important that these be understood by the implementer as well as the operator. There is one more question that needs to be answered. How would the control system go about determining the system load that will be used for the basis of this control? There are several ways that can be implemented effectively. The ones shown here are the most generic. We've referenced ASHRAE Guideline 22 because it contains an excellent set of requirements and recommendations for measuring chiller plant capacity and efficiency. If the instruments required for accurate load determination are not designed into the plant, it can be very difficult to add them after the fact. There are other acceptable methods of capacity determination that can be implemented, some of which might be proprietary to one system or chiller type. You could even implement multiple methods and use them as validations of each other. The main thing to note here is to choose a method that is reliable, repeatable, and sustainable. Mick, we've mentioned the importance of understanding each component's operating limitations. Would you please dig a little deeper into that?
Surely. Now that we've discussed system optimization, we need to step back and understand the boundary limits. That is, when do we need to deviate from theoretical optimum control so that the components and system continue to operate properly? From a component standpoint, we'll examine the cooling tower, chiller, and pump boundaries. Then we'll discuss a couple system limits. The first limitation for a cooling tower is its approach to the outdoor wet bulb temperature. As the load is reduced, the approach temperature decreases, which allows colder leaving tower water temperature. Physics also tells us that at the same heat rejection load, as the wet bulb drops, the approach temperature actually increases. So that means that the water is colder, but not as cold as we might have guessed. The second limit is that the tower fan VSD will have a minimum speed. Probably the most important limit to consider is the minimum tower water flow rate. During normal operation, if flow over the tower drops too far, there's poor water distribution over the tower fill. Poor distribution leads to poor heat transfer and perhaps scaling. Another possible issue is when it's cold outside, too much tower heat transfer can result in ice formation. Follow the tower provider's guidance to keep this from occurring. Now, to their credit, today's tower providers are offering more options for reducing water flow rates while maintaining good heat transfer. So there are more alternatives for reduced flow today than there were even 5 or 10 years ago. Now, let's look next at the chiller. The first limits are easy: minimum and maximum condenser and evaporator water flow rates. The minima are to ensure good heat transfer and controllability. The maxima avoid tube erosion and vibration issues. Next, the compressor must overcome the pressure difference or lift from the evaporator refrigerant pressure to the condenser refrigerant pressure. For centrifugal compressors, if the lift is too high, the compressor may surge. As Lee mentioned, you want to avoid surge. On the other end of the spectrum, all centrifugal chiller manufacturers have a minimum lift requirement. This limits how far the tower water temperature may be depressed or chilled water temperature may be increased. From the literature we've seen, these requirements seem pretty similar for all the manufacturers. The condenser water pump limits either its minimum speed or the highest of 3 flow rate limits. We already discussed the cooling tower and chiller condenser minimum flow rate limits. A third possible limit is that there will be a speed below which the condenser water pump will no longer be able to overcome the open portion of its loop, that is, from the basin of the cooling tower to the top of the cooling tower. For each application, the minimum flow rate and pump speed must be determined using the highest of these three limits. Finally, the chilled water pump variable speed drive has a minimum speed. Also, the chiller evaporator has its minimum flow rate. The system and its control must provide a method for flow to remain above that minimum flow rate. We've discussed this in previous E&Ls on variable primary flow, and there are many system operations that result in component limit violation. We'll take the time today to cover two system limits. During humid conditions, at reduced load, if the condenser water pump and cooling tower fan speeds are reduced too quickly, it's easy to send a chiller into surge. Another limit is experienced if the tower flow rate drops too far and heat exchanger effectiveness drops. If this occurs, the condenser water temperature and the chiller condenser pressure rise significantly. This can cause an increase in system energy usage. Lee, what's next?
It's obvious that understanding system operation and the component operating limits Mick just discussed for each specific installation is imperative for the team installing and commissioning the system. It is no less important for the system operators. They need tools to operate these systems sustainably, both for daily interaction as well as ongoing fine-tuning. To that end, a concept that is emerging in the industry is that of user dashboards. Historically, control systems have had equipment and system graphics overlaid with pertinent data. The differentiating concept between dashboards is not to just present data, but to turn that data into actionable knowledge. Some of these screens may have graphics that look familiar, but the content is different. In fact, very often there are dashboards targeted at specific users. What a daily operator needs to know to keep a building operating effectively is different from what a facility manager or energy engineer would be interested in. As we all know, the operator is the final judge and jury of the viability of any control method. If they don't understand it and accept it, the system is soon doomed to manual operation. A system operation dashboard might include a simplified representation of optimized performance and other pertinent system performance calculations. Metrics such as system temperatures, pressure, cooling load, as well as system kW per ton versus ideal and system reset values would be valuable. One of the challenges operators face is understanding if the optimization strategies are functioning properly. And if not, what is not working as it should be? Since we've discussed the importance of proper energy intensity balance between components, a plot of the current state of component operation would not only assure the operator of acceptable operation, but could identify and further diagnose any operating imbalance. Enabling user interaction supports sustainable operation. The goal of any chiller plant control system should be to meet the building load. But there are times in the life of any building that the operator needs to respond to unusual demands that the plant control system may not be able to identify. Too often, they feel the only recourse is to go out to the plant and start to put things in manual control that often never get set back to auto. A concept to alleviate this manual override response is the addition of a system mode selector. Such a selector would allow an operator with proper authority to change the system operating sequence from full optimization to enhanced cooling or emergency cooling for a set override period of time. The two override modes reduce and eliminate the optimization resets respectively to ensure the maximum flow of the coolest chilled water possible is available to the building. Such operation would be noted in the system control log as well as totalized override time each month. If such operation is initiated too often, it may be an indication that the system sequence needs to be changed. A building system problem needs to be addressed, or possibly that there is a need for operator training so that they are more comfortable with the normally optimized operation. As for the operator, a system mode dashboard that actively shows not only the operating mode the plant is in, but also the operating set points and conditions for key system components should be available. Think of this as a real-time sequence of operation that helps the operator understand precisely how the system is supposed to be operating, and therefore, if it's operating properly. Experience has shown this, too, can be a positive step towards sustained performance. A facility manager would like to know that the whole building is operating properly. As such, a dashboard that brings together relevant operating metrics for the air systems as well as the chilled water system rolled up into whole building performance is valuable. From a chiller plant perspective, it should point out things in the building that might affect plant performance, such as each air system's chilled water delta T. Pointing out an air handler that is causing low delta T as soon as possible allows the facility manager to address it before it becomes systemic. The phrase "follow the money" comes to mind. Also on the facility manager's dashboard would be information related to the cost of running the plant and the projected dollars being saved by the optimization. For the energy engineer, these would include KW, KWH, and energy cost savings based on individual and rolled up energy saving strategies. Of course, trending of important metrics should be available for all users. That's a brief overview of some useful system dashboarding concepts. Susanna, we've talked a lot about optimal design and control of new chilled water plants leveraging variable speed technologies. What are your thoughts on applying this to existing plants?
Thanks, Lee. So now many of you may be asking, what can I do to my existing system? Can I apply some or all of these concepts to the equipment I already have in the system I already have? Now, a lot of the time you're asking this question when you're considering doing something to your chilled water system. What equipment have you inherited? Are you going to have to keep it? And what have you decided already to replace? Aging equipment, items that need too much maintenance, or that are too inefficient today? To answer the first two questions, you have to consider the third. What are the constraints of the original design? Do you have the original design in actual operation today? For example, you have 3 chillers in parallel before, but one of them was a swing chiller. Having different sized chillers in an all-variable speed plant complicates things because of the different limits, and I would advise against dynamic condenser flow control in an asymmetric chiller plant. Adding variable flow to a high flow system, for example a 3 GPM per ton system, turns it into a lower flow system at least some of the time. The first constraint you run into as you turn down the condenser water flow, in all likelihood, is a chiller limit. As I said, this is likely the first constraint, but probably not the only one. Finding constraints on an existing chiller may be unnecessary because many times this conversation comes up when a new chiller is being selected. This opens the door to a lot more options. Chances are good, though, that you'll be asked to preserve some old chillers while either upgrading or buying new chillers that sit next to them. And so your design and operating sequence of operation would need to accommodate a mix of variable and constant speed chillers and/or a combination of chillers that have different limits. Before you pass go and collect $200, your first calls are to the original equipment manufacturers to find out the theoretical limits of your equipment. So you'd call the chiller, tower, and pump manufacturers, and hopefully also the engineers of record on past plant designs. The other thing you may have going for you on an existing chiller plant is that you don't have to wonder about actual system limits. You have equipment there that can help you find the limits in reality rather than theory. For example, turn the condenser flow down until the chiller starts to approach surge. This would be the stall region, which does not harm the chiller, but it does start to make noises you're hopefully not accustomed to. The less noticeable effect would be in tower performance. Is the fill starting to get dry in spots? Is there a flow when the tower performance starts to drop off noticeably? And what about the limits on the condenser pump? If you already have a variable speed drive on the pump or a throttling valve, what happens when you turn it down? What if the chiller was originally selected for 2 GPM per ton, but for whatever reason the operator gave it 3 GPM per ton? If you turn down the condenser flow, you might not ever get that chiller to complain. Maybe it's the pump that starts to make noise first, or the net positive suction head starts to get too low. If the condenser pump doesn't already have a variable speed drive, is the pump motor rated for it? You might be looking at a new pump and motor suitable for application with a variable speed drive. Now, generally speaking, centrifugal chillers selected for 2 GPM per ton can run at 3, but chillers selected for 3 GPM per ton probably encounter limits when trying to run at 2, at some combinations of chiller load and wet bulb conditions. What else are you doing at this time? Can you get a tower with a tighter approach temperature? For example, changing from a 7-degree approach to a 5-degree approach? The tower will be larger, but it may help your existing chillers tolerate a reduction in condenser water flow. Can you modify the chiller? There may be additional amps available on the motor that was selected for your chiller, but you have a nameplate today that corresponds to the original selection point, not the maximum operating point on the motor. Only the chiller manufacturer can help you find out if a reselection like this is possible without a physical modification to the chiller. At some conditions, you may be able to trade chilled water reset for additional lift capability when you absolutely must have it. And then, suppose you have to decide between new chillers and new towers, at least for right now. You can probably get the lift capability that you need for reducing condenser flow rates in either component, so unless your chillers are really old or have little extra lift available. The important thing to realize is that for an existing tower, when you send it warmer water, it comes back colder. The effectiveness improves when the initial temperature difference is higher. The only way to hold tons constant is to lower the flow rate. To rebalance an existing tower with a chiller at a lower flow rate but at the same load, it leads to something like this chart. For a tower originally selected for 3 GPM per ton and 85-degree leaving water temperature, dropping to 2 GPM per ton gives us 97.5 degree water entering the tower instead of 94.5 and 83.3 degree water leaving the tower, increasing its delta T or range by nearly 5 degrees. Let's bring back up mix charts. Not all the options he showed are available in an existing plant that's reusing one or more centrifugal chillers. Suppose you have an all-constant speed chiller plant today with 3 GPM per ton on the condenser side, and your mission is to reuse the 2 chillers. Let's assume you're starting with average chillers, when they were purchased in 1999 or later at 0.567 kW per ton without the drive, and the drive takes it to 0.585, the same assumptions that Mick used. Our options are to add drives to the tower fans, optimize the temperature control, add drives to the chillers, and or put a drive on the condenser pump. The constant 2 GPM per ton options are likely off the table, but we can control this plant into low flow most of the time using variable condenser water flow as our option. So let's throw some hypothetical costs at it, but full disclosure, I don't do any pricing, so your costs will surely be different. If we assume a cost of $50 per kW for the drive, plus installation, putting the drive on the chiller costs roughly $35,000, installed on the 575-ton Climate 5A hospital. For the tower fans, less than $3,000 installed. If we can reuse the condenser pumps, putting drives on them would be about the same as the tower fans. If we can't reuse the condenser pumps and motors, it will cost quite a bit more. Chiller tower optimization is a wild card. How capable are the existing chiller plant controls? Now, I've assumed that all alternatives are going to need a controls upgrade anyway. So, which other options can we eliminate? It sure looks like optimum tower temperature control, even on single-speed towers, is a no-brainer that allows us to unlock the other options. We're now down to 3 further levels of performance: variable speed tower fans, variable speed chillers and towers, or going all variable speed, including the condenser pumps. As I mentioned earlier, annualized kW per ton is not that helpful because there could be lots of part load hours and therefore lots of potential energy savings, or not as many part load hours. Either the economizers remove them, the climate and building specific, and not as much energy savings even though we started with a higher annualized kW per ton. Now this case looked at the Chicago hospital without an economizer. However, recall the mix showed the improvement trends are the same for the other building types in virtually all climates. So let's look at another building in a different climate. Here I've changed to the Albuquerque office building with an airside economizer. Those paybacks that could be as short as a few months are now several years. Even though we improved by 29% over a respectable base of 0.785 annualized kW per ton, going all variable speed won't save as much money due to the shortened cooling season and lower peak loads. The problem is that economizers and a milder climate take out many of the hours when the system is most efficient. The payback on our investments may simply not be favorable enough, and we may want to look for a less costly alternative or wait until we need to replace the chiller. The key is to identify the right opportunities, then compute rather than assume the returns on potential investments. So what are you looking for in an application? Where are the opportunities? The first one is to find an application with a lot of year-round load. This could be an application that is driven by a high amount of internal loads, or one that doesn't have an airside economizer to remove the loads when it's cold outside. Another potential candidate is an existing system with a high condenser flow rate, which I consider to be systems that have 2.8 GPM per ton on the condenser flow or higher. As we saw on mixed slides, the time is ripe when new chillers are going in. But even if you aren't installing a new chiller, if you control it properly, you can turn that high flow system into a low flow system a lot of the time. Another candidate, systems with constant speed cooling towers, or those with 2-speed fans. Drive retrofits on cooling tower fan motors are very economical for the benefit that they bring. They're also attractive as a retrofit on a 2-speed fan motor because the control won't hunt and the system will have better stability. Oversized plants are good places to look because not only is there extra chiller capacity, there is excess pumping capacity, which makes the auxiliary power a higher proportion of the total energy. They also have big pipes, so the pumping energy savings at low flow will not be reduced by the temptation to reduce pipe size and trade in some of the energy savings for first cost savings. And don't overlook the potential in constant speed single chiller installations. The ancillary power quickly dwarfs chiller power in these systems at part load, and they experience the drop-off in chiller efficiency more acutely at part load. These two factors combine to create excellent applications for retrofits. Using advanced controls, single chiller installations can have similar performance to multiple chiller plants. The final thought I'll leave you with today is the opportunity to go all variable speed on your chiller plant anytime you're installing a new air-cooled chiller. The new generation of air-cooled chillers have variable speed compressors and condenser fans and support variable evaporator water flow. This means that all of the optimization we're discussing today for water-cooled systems is in the box, and the chiller controls handle all of this complexity already. Jeannie?
Today we took a historical look at usage of variable speed in chiller plants. We looked at the opportunity for savings in some example configurations and dove into plant operation and control considerations. What we learned today is there are complexities to consider, and when properly designed and controlled, an all-variable speed chiller plant offers the opportunity for significant energy savings. Now, there are a number of publications available that provide more information on the material covered today, including a recently published Engineers Newsletter. A bibliography detailing these resources is included in your handout. Additionally, past broadcasts, as always, are available on DVD at trane.com/ENL. Many are accredited for continuing education and are available on demand, free of charge. Visit trane.com/continuing-education for a complete list to satisfy credentialing requirements. Many are lead specific. And remember to fill out a survey and let us know how we're doing. AIA members, please remember to turn in your information to your local site coordinator. And finally, please ask your local host about details for the 2014 Engineers Newsletter Live programs. Early next year, we'll provide an overview of LEED version 4. In spring, we'll discuss applying variable refrigerant flow, and we'll return in fall to discuss chilled water terminal systems, so please plan to join us. Thanks for your time today. We look forward to seeing you next year.